Hello, hello, hello. This is Introduction to Coding Theory Problem Solving session for week 7. I am your teaching assistant Sachin from the Indian Institute of Science, EC department. This is the penultimate week. There are only 2 weeks left, including this one, so I expect uh, most students to not show up to the live classes. On top of that, today is a very important festival for Indians called Ganesha Chaturthi, so nobody might show up today who would skip such an important festival for a class. Well, the good thing is that the recording will be uploaded on YouTube. So if you are hearing this, you're probably watching this on YouTube. Hopefully, this is helpful to you. Let me join the meeting through my tablet and then share my screen from there. Week 7, let's start off with the first question. Max star of x plus 2y comma y plus 2z is equal to what? So in the lecture, we define uh, definition max star of x comma y is natural logarithm of e power x plus e power y. So max star of x plus 2y comma y plus 2z is natural logarithm of e power x plus 2y plus e power y plus 2z. I can take e power y common in those two terms and write that as e power y times e power x plus y plus e to the power 2z, and log of products log of a product is equal to the sum of the logs. So this is nothing but log of e power y plus log of e power x plus y plus e power 2z. Natural log of e power y is y. So we get y plus natural logarithm of e power x plus y plus e power 2z. And we can't simplify any further, so that is what max star of x plus 2y comma y plus 2z will be equal to. If you have options, this was actually a multiple choice question. I have not given you options, that's all. So if you have options, you will match whichever option it is and mark that as the right option. Okay. Now this is supposed to be a 2 hour session. My first question, I solved it in 2 minutes. I have only 10 questions. So if I go about at my usual pace, especially since there are no live viewers, the session can be finished in half an hour. And then I'll have to blabber on about random stuff for the remaining 1.5 hours. So instead of that, I'll do a small experiment. I'll just go away for a few minutes and then come back. Let's see if anybody is even watching these videos. Just a small test for my personal curiosity. Of course, since I'm doing this, I'll add timestamps to the exact location of the questions. So if someone is actually seriously watching my videos, then you can move to the correct timestamp for the next question. Okay, let's go to question two. Given a rate R equals 1 over 3 turbo code, and how do we get this turbo code? We get this by connecting to rate R is equal to 1 over 2 convolutional encoders. So these are the constituent encoders of the turbo code, and the generator matrix is 1 over 1 plus D for the constituent convolutional encoder. For the block length n equals 6 and interleaving pattern given by phi of I equals to 50431 is used. What is the output of the interleaver? So in this question, they're asking the output of the interleaver, not the output of the encoder. You have to be careful. If you read this too fast and don't read the question properly, then you might think of it as a standard question where you are asked, given an information sequence and asked to give the output. You might be tempted to write the output sequence. That's not what they want. For this question, they want output of the interleaver corresponding to input sequence 01100. Okay, so for g of d is equal to 1 and 1 over 1 plus t, this will be what the convolution encoder will be. So these are systematic convolution encoders. The first bit will be the input given as is. Then the second output code word is from the first convolutional encoder, which is of this form. So use a recursive encoder with the feedback, and that's your second code word bit. So you're using identical convolutional encoder blocks. So the third code word bit will also be the same, except a small change. The input is actually interleaved. So here as an interleaver pi shall interleave the information bits in a block and send it to the same structured convolutional encoder. So that will be your third bit. So this interleaver is an important part here. Okay, that's the difference between just normal convolutional encoder as opposed to a turbo encoder. Now, so there are to answer this particular question, there are six, 1, 2, 3, 4, 5, a block of 6 bits, and the given sequence is 0, 1, 1, 1, 0, 0. So it's 0, 1, 1, 1, 0, 0, and what's here is the position value, and what's here is the actual value of the bits. Now the interleaver will rearrange this. So the way it rearranges is 250431. So the bit in position 2 will come first, then the bit in position 5, then the bit in position 0, and 4, 3, and 1. So the bit in position 2 is 1, bit in position 5 is 0, next 0. Bit in position 4 is also a 0. Bit in positions 3 and 1 are both ones. So it will take a block and change the position of the bits in that block. That's what the interleaver does. This is your answer. The previous question, this was your answer. Okay, that's it about question 2, but this is a continuous type of question. So the same thing, same encoder is used for the questions that come next. So all this is actually useful for that. Okay, I'll take another short break and come back for question 3. Okay, let's go to question 3. Question number 3. What is what is the output of the turbo encoder given in question 2, assuming both the encoders were in all zero state? Okay, so there's only one memory element. So the state is either 0 or 1. Okay, so this if this is in state 0 and I give an input 0, I change the state to 0 itself. So this input 0 is moved into the memory element in the next time instant. So the state will change to 0. So the next state is nothing but your input added to your current state. And your output is your current state, is also the input added to your current state. So if you're in state 0 and your input is 0, then you go to state 0 and give out an output 0. You're in state 0 and your input is 1, you go to state 1 next. Your output is 1. If you're in state 1 instead and your input is 0, you go to state 0 and your output is 1. And if you're in state 1 and your input is 1, your output is 1 XOR 1. 1 added to 1, 1 more, 1 plus 1 more 2, which is 0. Next state is also 0. This can be captured in a state diagram as if you are in state 0 or if you're in state 1, stay in that state. Or you can go to the other state. So in state 0, so one other thing is the output of the the output of this block is what I was talking about earlier. But the convolutional encoder, the constituent convolutional encoder, contains the entire thing. So we studied convolutional encoders in the previous lecture. So this is a systematic convolutional encoder. So one of the output bits is the same as the input. So when you're writing the output in the state diagram, you have to write the set of two bits together as the output. So this will follow your input. This will follow your input as well as the stored state. So If the state was 0 and your input was 0, then here you would have a 0 and here you would have a 0. So the total output of one of these convolutional encoders, that is this, would be 0, 0. Similarly, the input of this convolutional encoder is also 0, 0. So these are two convolutional encoders in parallel. Since they are systematic, we are using the same code word bit for both of the convolution encoders for the systematic part. So we won't have another code word that will be connected to your input. So for the systematic part of both the convolutional encoders, there's only one output. So that would mean in our state diagram, the output from state 0, if your input bit was 0, is 0, 0. If your input bit was 1, then it would be 1, 1. Similarly, in state 1, if your input was 0, it would stay in state 0, state 1, because your next state is the sum of your current state and your input. So you'll stay in state 1, but the first output is 0, second output is 1. So the final branch is 1 slash 1 0. So that's the state diagram for one of the constituent convolutional encoders. Now the input sequence is uh, for encoder 1, input 0 1 1 1 0 0, give output from the state diagram. We can tell first you give you're in state 0. First input is 0, so you are still in state 0 and your output is 0 0. So you get 0 0. And if you take only the non-systematic part of that, it will be 0. Now you're still in state 0 and your input is 1, so you'll go to state 1, your output will be 1. Now you're in state 1 and your input is 1, so you go to state 0 and your output is 0. Then state 0, your input is 1, so you go to state 1 and your output is 1. Now you're in state 1 and your input is 0, so you stay in state 1, output is 1. Again, the final input is 0, so stay in state 1 and output is 1. For encoder 2, the input is interleaved. So the interleaved input is what we had in the previous question, 1 triple 0 double 1. So 1 triple 0 double 1, that will give you the output. So you are in state 0, you get a 1, no, your output is 1, you go to state 1. You get a 0, you stay in state 1, get an output 1. Again, a 0, another 0, so 1, 1, 1, 1. Now you're in state 1 and your input is 1, so you go to state 0 with an output 0. And again, your next input is 1, so you go to state 1 with output 1. 4 0, 4 1s, a 0 and a 1. Now, the systematic part, V0 is nothing but U, is nothing but 0 1 1 0 0. So, output sequence is the first bit of all three of these sequences put together. So, it's 0, 0, 1, 0, 0, 1. Next is 1, 1, 1. So next you'll get 1, 1, 1. Next you'll get 1, 0, 1. Then 1, 1, 1 again. Next is 0, 1, 0. Next is 0, 1, 1. So that is your output sequence for the convolutional encode for the turbo encoder. Question 4 asks for the rate R is equal to 1 by 3 turbo encoder given in question 2. Bits are mapped according to the 0 goes to -1 and 1 goes to +1. An input sequence of 4 bits is encoded and transmitted over AWGN channel for an AWGN channel. Received sequence vector R is 0.8, 0.1, -1.8, then 1.0, -0.5, 1.2, -1.8, 1.1, 0.1, finally 1.6, -1.6, -1.1. Assume that the channel SNR is ES over N naught is 1 over 4, and initially the encoder was in the all zero state. Calculate the value of alpha 1 star of S0 for the decoder 1 at the first iteration. If the R0 is 0.8, 0.1 and vector V0, which is what was transmitted as -1, -1. So from lecture, you would have seen the formula for alpha L plus 1 of S0 in terms of gamma L of alpha L plus 1 of a state S in terms of gamma L of S prime comma S plus alpha L of S, where S prime is all the states at time L. So in the log domain, it will be alpha L plus 1 star of S prime is gamma L star of S comma S prime plus alpha L star of S, something of that sort. So alpha L plus 1 star of a state S is by definition log of alpha L plus 1 of S is max star, which we had seen in the first question, for all states S prime in sigma L, where sigma L is all the set of states that you can be in at time instant L. Gamma L star of S prime to S plus alpha L star of S prime. It's a recursive definition. So you have to initialize at time 0 alpha 0 of alpha 0. So forward matrix initialization alpha star or alpha 0 star of S is by definition log of alpha 0 of S, which is by definition 0 if the state is the all 0 state and minus infinity if the state is not the all 0 state. So here S0, if you take that as the initial state, it's the all 0 state they have given. The encoder was in the all 0 state initially. So alpha 0 star of S0 is 0, right? Now at L equals 1, sigma L has only, so at L equals, sorry, instead of 1, it should be 0. At L equals 0, sigma L is nothing but S0. So time instant 0 initial time. If we started off in the all 0 state, so that's the only state in sigma 0 is the set S0. So that's the only state. So when you apply that to the formula, the first formula, alpha L plus 1 star of S, for L is equal to 0, you get alpha 1 star of S0. So in place of S, you have to write, okay, so here you have max star of uh, gamma L star plus alpha L star, but for all S prime in gamma, sigma L, but S prime can only be S0 because sigma L or sigma 0 has only state S0. So you get that max part is not there. So you get gamma 0 star of S0 comma S is this S is S0 here. So gamma 0 star of S0 comma S0 plus alpha 0 star of S0, which is nothing but gamma 0 star of S0 comma S0, because from here we see that this is 0. Now the definition for gamma L star of S prime comma S is, have to go back and check the lecture. This is by definition equal to log of gamma L of S prime comma S, which is equal to UL LA of UL. UL is the information bit at time L. LA of UL is the a posteriori probability. Log likelihood ratio, the log of natural log of probability that UL is equal to 1 divided by probability of probability that UL is equal to minus 1. So that's LA of UL plus LC by 2 of RL dot VL, where LC is the channel, what do you call it? Channel reliability factor, which is equal to, so LC is equal to 4 times ES over N naught. But ES over N naught, according to our question, is equal to 1 over 4. So this is 4 times 1 over 4, which is equal to 1. Since no a priori, sorry, I think I said LA of UL is the a posteriori log likelihood ratio, but it's the a priori log likelihood ratio. Since no a priori information is known for the first iteration, we assume all values are equally likely. That is, we assume probability of UL is equal to plus 1 is equal to probability of UL is equal to minus 1. So the ratio of P of UL equals plus 1 by P of UL equals minus 1 is 1, and log of that is 0. So that is LA of UL is equal to 0. So gamma L star S prime comma S is equal to half of RL dot VL. That would mean that alpha 1 star of S0 is half of R0 dot V0. R0, they have given the first, for the decoder 1, the first received vector. So the total received vector, the first bits, first the bits at time instant 0 in the received vector are 0.8, 0.1, minus 1, 0.8. So zero point 0.8 is the systematic part, 0.1 is from the first encoder, and minus 0.8, 1.8 is from the second encoder. Since we are dealing with only decoder 1, received vector is 0.8, 0.1 at time instant L is equal to 0, and then V0 is given as minus 1 comma minus 1. So this is nothing but 0.8, 0.1 dotted with minus 1 comma minus 1. So it's point minus 0.8 minus 0.1, which is minus zero point 0.9 by 2, which is minus 0.45. That's it. I'll take a break and come back and do question 5. All right, let's come to question 5. Consider the same turbo encoder as mentioned in question 4. Bits are mapped according to the rule 0 goes to -1 and 1 goes to +1. An input sequence of 4 bits is encoded and transmitted over an AWGN channel. Received sequence vector R is 0.8, 0.1, -1.8, 1.0, -0.5, 1.2, -1.8, 1.1, 0.0, 0.1, 1.6, -1.6, -1.1. Same sequence as in question 4. Assume that the channel SNR is also the same. ES by N0 is 1 over 4. Calculate the value of, so for the same values as in Q4, calculate the value of beta 3 star of F0 for R3 here is 1.6 comma minus 1.6 and V3 is -1 comma -1. Assume that the encoder is terminated to all zero state at time t equals 4. So again, here instead of alpha, we're asked to find beta, and it's the first iteration. So in beta, you go from time the terminated time t is equal to 4 and calculate backwards. These are backward metrics. So beta L star and the state S prime is by definition log of beta L of S prime. You have to go back to week 5 or something for the BCJR algorithm. This is the BCJR algorithm, except that it is in log now, and we had earlier studied in the without logarithms. So max star S belongs to sigma L plus 1, gamma L star of S prime comma S plus beta L plus 1 star of S. Now backward matrix initialization beta k star is log of beta k of S. 0 if the state S is the all zero state, and minus infinity the state is not the all zero state. So here the algorithm terminates at t is equal to 4, so k is 4, so beta 4 star of S is, and the state we want to look at is the state S0 is the all zero state. So beta 4 star of S0 is 0. Now from here you get beta 3 star of the state S0 is, so in place of S prime you have to put S0. So S prime is the state, the all zero state. Again, max star of S in sigma L plus 1. Sigma L plus 1 is sigma 4, and at time instant 4 we are terminating the algorithm by setting everything to 0. So there's only one state in sigma 4, which is the state as 0. So that's only one term. So there's no, that max is not applicable in this iteration. So you get gamma L star of gamma 3 star of instead of S prime, you have S0, and S belongs to sigma 4, which is also S0, plus beta 4 star of S0. And we know that beta 4 star of S0 is 0. Now we are left with gamma 3 star of S0 comma 0. From the previous question, we saw gamma L star of S prime comma S is half of RL dot VL. The first iteration LA of UL is 0. And for this question, LC is 1. So this is nothing but half of L is 3, so it's R3 dot V3. So nothing but half of R3 is given to be 1.6 comma minus 1.6, and V3 is minus 1 comma minus 1. So it's half minus 1.6 plus 1.6, which is 0. So here this is the dot product, same dot product. So that's it. That's your beta 3 of beta 3 star of S0. Question 6. Sorry, I had throat infection. I have throat infection. I have had throat infections since 10 days. Question 6. Which of the following statements is incorrect regarding turbo codes? First statement is the performance in waterfall region is governed by the convergence behavior of the constituent encoder under iterative decoding algorithm. You should must have seen the bit error rate versus SNR graph. So this is the waterfall region, and that region it is true that the performance depends on your encoder behavior, and the performance in this is the waterfall and this is the error floor region where the performance is depends on the spectrum of the turbo code. Statement B is systematic encoders have better performance where this is true. Better performance in the waterfall region compared to the equivalent non-systematic encoders. It's also a true statement. See the performance in error floor region is governed by the distance spectrum of the turbo code. D, none of the above. So, as I said earlier, this is also true. In error flow region, the performance depends on the spectrum. So, none of the above is a false statement. All the statements are true. Okay. Now we'll move on to question 7, 8, 9, and 10. These questions are simply theoretical. There's nothing much to explain. You just have to go to the lectures and see the explanations yourself. Which of the following statements is incorrect? A. Recursive encoders are feedback encoders. That's correct. D. Systematic encoders have better convergence at low signal to noise ratio. That's also correct. Then, so the low signal to noise ratio region is the waterfall region where performance depends on the convergence behavior of the constituent encoders. So systematic encoders have better, and we saw the systematic encoders were better performance in the waterfall region. Yes, it's the same question again, or same statement again, stated in a different way. Here it says waterfall region, here it says low signal to noise ratio, but the waterfall region is in the low signal to noise ratio region. Thirdly, turbo codes have a small decoding delay. That is, that's false. That's incorrect. D is none of the above. So this is a smaller size. And they give the final option as none of the above. One of the options is incorrect, as we have seen in this question. Two options are correct, one of them is incorrect. By none of the above they mean none of the above is incorrect, right? Is that statement incorrect or correct? Because one of the other statements is incorrect. So the statement none of the above is incorrect is also incorrect. So option D is also an incorrect option. I don't think anyone has really thought it through when they give none of the above as an option. And maybe it's just too obvious. we let it pass, but technically none of the above is also an incorrect option because one of the above is actually incorrect. Well, that comes out more like sophistry than any pragmatic use. So let me just move on. For a rate R equals one third turbo core, what is the correct expression for computation of extrinsic information at the output of decoder 1? Answer is LE at the decoder 1 of UL is L of UL minus LC RL plus LEUL at the decoder 2. So here L1 of UL, so that's the expression. But what does it mean? L1 of UL at the first decoder is the log likelihood ratio log of probability that UL is plus 1 given your received vector R1 and a priori probability LA of 1 divided by probability UL is minus 1 given the received vector R1 and a priori probability LA of 1. So this L1 of UL contains is affected by the received word, received vector, and the a priori probability. So if you want to subtract that and independent of the received word and whatever a priori probability you have assigned LA of 1. If you want to give an estimate of the log likelihood ratio, so you have to subtract the contribution from RL and LA. So, but the thing is, the a priori probability after the first iteration at least is nothing but the extrinsic L value from the decoder 2. So for the first decoder, the extrinsic L value is used as the a priority probability, and for the second decoder, the extrinsic value of the first decoder is used as its a priori probability. That's why you are subtracting LCRL of 0 and LE2 of UL. LE2 of UL is the eccentric L value of the second decoder, which is actually used as the intrinsic a priori probability for the first decoder in the next iteration. So that is the LE1 of UL, the extrinsic information at the output of decoder 1. You take this and feed it as the a priori probability LA for the second decoder in the next iteration. So LA of 2 will be LE1 of UL. So it's an estimate of the extrinsic a priori. It's not uh, a priori, it's extrinsic a posteriori L value, LE of UL, is passed as the input to decoder 2 as its a priori value, LA2 of UL. So LE1 of UL after interleaving, of course, is passed to decoder 2 as its a priori probability LA2 of UL. Okay, we are done with that question. Question 8. So next we move on to question 9. Which of the following statements is incorrect? Turbo codes are parallel, concatenated, convolutional codes. Saw an example earlier. It's a correct statement. Turbo codes perform very well. High signal to noise ratio. So from the graph that's not true. It's incorrect because at high SNR we are in the error floor region, and regardless of the increase in SNR, your BAR stays about the same. Can't get better performance by increasing higher using more SNR. Block codes can also be used as constituent codes in turbo encoders. That is correct. You don't have to use convolutional encoders. Finally, turbo codes can achieve performance close to the Shannon limit. That's also correct. That's why in all your communication applications, everything is set up to use turbo codes. And since everybody is already using turbo codes which are close to the Shannon limit, even if you make a new code that has slightly better performance than turbo codes, no one would be interested because all the framework would have to be changed to implement your new code. Who would bother doing that if your gains are marginal? So unless you find new ways, some new applications, any code which you come up with is just useless. There's no it's going to change their entire infrastructure and protocols and all just for small gains. This turbo is already close to the channel limit. Which of the following statements is incorrect for an interleaver? Interleaver changes the weight of the input sequence. We saw an example of what an interleaver does. It only repositions the ones and zeros. So the number of ones in the information sequence doesn't change at all. So the weight of the input sequence also doesn't change. So right off the bat, that's the incorrect statement, and I would just leave this question. If it was an exam, I would mark that as incorrect and move on to the next question. Since this is not an exam, we'll look at the other options also. Pseudo random interleavers are good. That is true. State complexity of turbo codes is increased by the interleaver. That's also true. Interleaver affects the performance of turbo codes in the error flow region. That's also true. So we can be sure that only the first option is incorrect. All right, we are done with this week's problem solving. See you in week 8.